Hello everybody, welcome into another lesson. So today we are going to talk about some postulates and some theorems relating to points, lines, and planes. So here we have our very first postulate. It really has no name, but it is a geometry postulate. It states that a line contains at least 2 points, a plane contains at least 3 points not all in one line, and a space contains at least 4 points not all in one plane. So a line contains at least 2 points. Well, that's true. In order to form a line, you need at least 2 points in order to make the connection, right? That kind of demonstrates that a line contains at least 2 points. Very true. We'll call this point A. We'll call this point B. Now, a line can have more than 2 points, but it contains at least 2 points. If you only have 1 point, you can only prove just that, a point. You can't prove whether there's a line going through it or not. Then it says a plane contains at least 3 points, not all in one line. So let's go ahead and draw ourselves a plane here. Let's draw a plane around the line, which the line will be on the plane. Let's put a point C right here that's off the line. If point C were on this line AB, we could only prove there's a line. We couldn't prove that there's a plane. So, yeah, it kind of goes back to what we were talking about in previous lessons. A plane contains at least 3 points not all in one line. Basically, this is a postulate given the definition of a line, a plane, and a space. That's really all it's doing here. And then we have a space contains at least 4 points, not all in one plane. So let me draw another plane here overlapping this one so we can set up a space. We have another plane. We'll put some arbitrary point D in this next plane. Let's call this plane plane A. We'll call this plane plane B. Alright? Well, had point D been in plane A, all we could prove is one plane. We couldn't prove a space. But point D lies in plane B. We have the other planes in point A. Together, these make up a space because you have multiple planes with multiple points in between them. So that's all this postulate states. So to recap, a line contains at least 2 points, line AB. A plane contains at least 3 points, not all in one line. So you have plane A with line AB and then point C outside of line AB. And then a space contains at least 4 points, not all in one plane. So you have plane A with line AB, point C out of line AB, and then in plane B you have point D. So that's this postulate at work for you. I'm going to let everyone catch up for a minute, then I'm going to go on to the next one. Alright. Let's go ahead, move on to the next postulate. There are several postulates and then 3 theorems being introduced today. Good news is today the 3 theorems we aren't going to prove. We're kind of just going to accept them like postulates. Because in this class we are not going to prove every single theorem we get, but we're going to prove a majority of them. Alright. This next postulate should be pretty easy. Through any 2 points, there is exactly one line. Through any 2 points, there is exactly one line. Well, we've already kind of stated it in other terms. We got our points here. You have point A, point B. Through these 2 points, there is exactly one line. because that's the bare minimum of points you need to make a line. So through any 2 points, there is exactly one line. Even when we were doing algebra and before that, when we were plotting points on the coordinate plane, all you needed were 2 points and you could graph the line on the coordinate plane, right? Well, this kind of states that. Through any 2 points, there is exactly one line. That's pretty self-explanatory. I would say that's a pretty easy one. Okay. Let's see, next postulate. Through any 3 points, there is at least one plane. And then through any 3 non-collinear points, there is exactly, let me underline exactly, one plane. Alright, so through any 3 points there is at least one plane. Through any 3 non-collinear points there is exactly one plane. Okay, so what this is here, let's draw some examples here. So let's say I have a plane, right? I'll call this plane A. So I'm going to draw line AB. Let's draw again line AB in plane A. Through any 3 points, there is at least one plane. Now, granted, I have a plane here with line AB, but what if here in plane B, I decide I'm going to put point C. Now we have a separate plane, we have point C. This just states through any 3 points there is at least one plane. That means there could be more. At least, of course, implies there could be more. We have a third point that's not even in plane A. So that demonstrates there could be at least one plane. Now, let's get rid of this plane. Let's go on to the other part of the postulate here that we want to talk about. The other part of the postulate is through any 3 non-collinear points, there is exactly one plane. So point C is now also in plane A. Well, we have exactly one plane because all 3 of these points are in plane A. And again, these are basically different ways of wording the definitions of plane, lines, points, spaces, but these are formally through postulates. So it's just basically, this is kind of a recap of what we've talked about. Let's talk about the next postulate. If 2 points are in a plane, then the line that contains those points is in that plane. Alright, so if 2 points are in a plane, then the line that contains those points are in that plane. The line that contains those points is in that plane, rather. So, let's start out. Let's draw another lovely plane. I'll put point A here, point B here. So, I'll call this plane E. We'll call this plane E. So, I have points A and B that lie in plane E. Well, we already know through any 2 points is a line, right? This ties in with that, so therefore line AB lies in plane E. Yes. In fact, we're gonna magnify this a bit, because a space contains 2 planes, right? Well, a plane contains 2 points not all in one line. So a plane definitely contains a line. A line contains a point. Well, that means that a point is in a plane already. A line's in a plane already. It's always going to be in a plane, and it's always going to be in a space. So based on what we've learned so far, we know a line will always be in at least one plane. So will a point, and a plane will always be part of a space. And then all those will be part of a space. So they're kind of all part of each other. Alright, last postulate. This one states, if 2 planes intersect, and so if 2 planes intersect, then their intersection is a line. Alright, so we've kind of already demonstrated this with our diagrams we've done in previous lessons, but this postulate states if 2 planes intersect, then their intersection is a line. So let's demonstrate that here. Let me draw this one here. We'll call this plane A. Let's draw another one here. We'll call this plane B. And let's plot some, just so we can name the line here, let's plot some points. I'll call this point C, I'll call this point D. Well, yes, we have plane A, plane B. They intersect at point C and D, or line CD. They intersect at line CD. So yes, this demonstrates that if 2 planes intersect, then their intersection's a line. Just like if 2 lines intersect, they intersect at one point. Well, if 2 planes intersect, they intersect at one line. Alright, now we have 3 theorems, which will be based on the postulates that we've learned. Good news for everyone here today, we're not going to prove these theorems. So here's the first theorem. This is how theorem is spelled. Alright, so that's how you spell theorem. It can also be abbreviated THM, period. You'll see that for theorem a lot too in geometry. This theorem states if two lines intersect, then they intersect at exactly 1 point. So this theorem is if two lines intersect, then they intersect at exactly 1 point. So let's see here. Let's draw a line. We'll call this line AB. Let's see. Draw another line going through AB. We'll call this C, D. They'll intersect at E. Alright, so I have line AB, and then line CD intersects at point E. Well, this demonstrates the theorem. A line intersects at exactly 1 point. If it's a straight line, think about it. It couldn't intersect at more than 1 point. It couldn't. The only other possibility is if line CD goes straight through line AB, which would mean it's really the same line. If it intersects at more than 1 point, it's not a line. You have a curve, which would therefore not be a line. So yes, if two lines intersect, then they intersect at exactly 1 point. So that's that theorem at work for you. All right, two more theorems. Through a line and a point not on the line, I don't need a comma, there is exactly one plane. Alright, so this next theorem states that through a line and a point not on a line, there is exactly one plane. So let's see. We're going to draw a line here. We'll call this line AB. Keeping it simple today, line AB. I'll put point C down here. So we have a line and a point not on that line. Well, there is exactly one plane. We'll call this plane D. Well, that kind of goes to the definition of a plane. This theorem is based off the definition of a plane. Like these three theorems we're doing today are so intuitive that we really don't need to prove them. We can just base them off of the definition of a plane, honestly, but that's what this theorem is stating. Through a line and a point not on the line, there is exactly one plane. But nonetheless, these theorems and postulates are going to be useful when we start proofs, which will be in a couple lessons. We are going to start doing proofs here very shortly, not today, but last theorem. If two lines intersect, then exactly one plane contains them. Alright, so this theorem states that if two lines intersect, then exactly one plane contains them. Well, let's see this at work here. Alright, I'm going to draw. I sure love A and B today. We'll do that. let's cross another line here. Call these points C and D, and for good purposes here, we'll say these two lines intersect at point E. Alright? Well, this theorem states that if two lines intersect, then exactly one plane contains them. Well, let's think about this a second here, okay? Let's just look at line AB. Forget about line CD. We have line AB, right? Well, points C and D, yes, they contain another line, but those are non-collinear points. Those are points outside of line AB. E is where they intersect, so you could argue it's on both lines. But let's look at points C and D. Those are non-collinear with line AB, and the definition of a plane is that a plane contains at least 3 points, not all in one line. So yes, this theorem kind of ties in with that. With that and the previous postulates. We'll call this plane F. So that actually makes sense. So we have one line here, but the other line, you could argue those are points that are not on the first line. And the definition of a plane is that it contains at least 2 points all on one line and at least another point not on the same line. So that's actually kind of intuitive. So this is picture proof here that if two lines intersect, then exactly one plane contains them. So that's really it for this lesson. This wasn't a super long one today, but it was very necessary. So next lesson, we're going to start our deductive reasoning unit, and then we're going to start getting into proofs. Next lesson, we're going to talk about if-then statements, biconditional statements, and converses. So it's really going to go more into logic than it even is geometry initially, but it is building into more geometry stuff. So I hope everyone has a good day. Take care.